In this screencast, we're going to consider now some applications of oxidation reduction processes. And a thing to note is when we start considering these applications, things like batteries and practical cells, you don't need to memorize all the possible examples, all these reactions, all these redox processes, and all the equations, but you should be able to interpret what's going on from the given equations. And certainly if you had access to a reduction potentials table with all the appropriate half reactions, the reduction half reactions, you should be able to figure out what's going on from that. So let's get going with example 10, which is a lead storage battery. It's the kind of battery that is in your car to start it. We'll do a lab dealing with lead storage batteries this week. And lead storage batteries are alternating sheets of lead and lead coated with lead oxide, and it's all bathed in sulfuric acid, which is the electrolyte. And typically lead storage batteries have multiple cells, and we will look at a single cell. The reactions that take place in a lead storage battery are the one that's shown on the screen and the second one that's shown on the screen. Notice they're a little more complicated than some of the oxidation reduction half reactions we've seen before, but we should still be able to track what's going on. Gaining of electrons, losing of electrons, potential for each half reaction. And then, of course, we can add things up. In this case, we don't have to do any multiplying because 2 electrons gained, 2 electrons lost, so adds up nicely to give us an overall cell potential under standard conditions of almost 2 volts, 1.924 volts, according to the values in your textbook. And given this, you should certainly be able to answer questions like the following. If we have a lead storage battery, what's the anode and what's the cathode? And I'll give you a moment, take a look at the process and see if you can answer this. And then, of course, we're going to note that lead oxide is what the solid is that undergoes gain of electrons or reduction, and the lead is the thing that undergoes loss of electrons or oxidation. Note that the lead oxide is actually coated on or packed with in a lead grid, and the lead grid that's just packed with lead is the other electrode. And in the case of this particular cell, the lead is where oxidation occurs, so that's the anode, and the lead oxide with the lead that holds it in place is where reduction occurs, and so that's the cathode. Now here are some useful electrochemical relationships that, again, you should know how to work with. Some of you in physics may have seen some of these things before. One of them we've seen already. The Faraday constant is essentially the charge of 1 mole of electrons. So 1 mole of electrons is 9.6485 times 10 to the 4th coulombs. We've also seen that a coulomb times a volt is a joule, and that amperes, A is the symbol for amperes, which is a unit of electric current, and 1 ampere is 1 coulomb per second, so a charge of 1 coulomb flowing past a particular location in 1 second. And then a watt, symbolized by W, is a joule per second. So watt is unit of power, joule is unit of energy, and energy per time, how much energy is produced or given off in a particular amount of time, that's a measure of power, so watts are joules per second. So let's look at an example that has several parts that will let us work with some of these relationships and do some calculations. Example 11, we have a single cell lead storage battery. So normal batteries have more than one cell, but we in this example just have a single cell battery. It's delivering a current of 1.50 amperes for 45 minutes. And the first question is, how many watts of electrical power are produced? And the relationships that we have to work with are shown on the screen. And of course, a good one to use if we want to find watts is an equation that gives us watts. So watts are joules per second, but joules are the same as coulombs times volts per second. And so that gives us some idea of what we should be doing. We're going to need coulombs times volts per second, and we look at what's given here, and well, let me see, we have minutes and we have amperes, but we also know that a lead storage battery is a 1.924 volt potential. And since a coulomb per second is the same as an ampere, so here's ampere equals coulombs per second. We started with watts equals joules per second. We note that a joule is a coulomb times a volt, and then we note that a coulomb per second is the same as an ampere. And so since the question gives us both amperes and we know from the previous example the voltage, we simply multiply those two together and we get 2.89 ampere volts. And then of course we like to report this as watts. So an ampere is the same as a coulomb per second, and then a coulomb times a volt is the same as a joule, and then a joule per second is the same as a watt. So how many watts of electrical power are produced is 2.89 watts. And notice we didn't use the 45 minutes because assuming the battery doesn't run down, if it continues delivering a current of 1.50 amps and has a voltage of 1.924 volts, then that product will be the number of watts being produced, and watts is the amount of energy per time. So it gives off that amount of energy every second, that number of joules every second, continuous power of that many watts until the battery runs down and some of those values would change. Okay, the second part of this question is how much energy is produced when this storage battery runs for 45 minutes, and we're asked to find the amount of energy in kilowatt hours. We know that watts are joules per second, so watts are energy per time. Therefore, energy, in this case joules, would be watts times seconds. We take this equation, multiply both sides by seconds, and we get joules equals watts times seconds. And if we wanted the energy in joules, we should therefore take the power in watts and multiply it by the number of seconds. So we'd convert 45 minutes into the appropriate number of seconds. But since we want the energy in kilowatt hours, we actually want to multiply by a time in hours. And so what we have is the energy is 2.89 watts, the power, times 0.750 hours, the amount of time that the cell was running. And that gives us the answer of 2.12, and the units are watt hours. So notice it's watts times hours. Nothing cancels out. And watt hours is a perfectly respectable energy unit. It's maybe a little weirder or less convenient than joules, but it's an acceptable energy unit. And this question asks for kilowatt hours. So since a watt is a thousandth of a kilowatt, then this becomes 0.00212 kilowatt hours. And if you notice in your electric bill, it's going to give your energy usage per month not in joules, but in kilowatt hours. So that'll be a product of the power that your appliances or whatever you're running in your house is using times how long it ran, but the power will be done in units of kilowatts and the time will be done in units of hours. And in the last part of this question, we're asked to determine how many grams of lead are converted to lead sulfate. Now, to do this, it's kind of helpful to remember the reactions that took place because we are going to need several things. It's going to be useful to know the overall cell potential or voltage, the amount of current, how long it ran. Notice here is the lead being converted into lead sulfate. Of course, lead oxide is also converted to lead sulfate, but that's not what we're being asked about. And it's also going to be useful to remember that 2 moles of electrons are being transferred in the process. So to solve this, we note that we had the cell running for 45 minutes. And then we are going to need to convert our minutes into seconds. So 60 seconds per every minute. And we're going to convert minutes into seconds because then we know the current in amperes, which is the same as coulombs per second. So we have 1.50 coulombs of charge that flows every second. So that allows us to cancel out seconds. And then every 1 mole of electrons has a charge of 9.6485 times 10 to the 4th coulombs, and so that lets us cancel out coulombs. And then, kind of running out of space here, so we'll keep going on the next line. Now we know that, going back to the chemical equation, for every 2 moles of electrons that are transferred, 1 mole of lead underwent conversion to lead sulfate. So our conversion here will be for every 1 mole of lead, there were 2 moles of electrons, and so that will convert moles of electrons into moles of lead. And then if you use the periodic table, 1 mole of lead is 207.2 grams. So that lets us convert moles of lead into grams of lead. And taking 45 times 60 times 1.50 divided by 9.6485 times 10 to the 4th divided by 2 and multiplied by 207 gives us a total overall final result of 4.35 grams of lead that was converted into lead sulfate. Notice, of course, other things happened. Lead oxide was also converted into lead sulfate, but we're only asked about the amount of lead that was converted into lead sulfate.